So first, some definitions, and some of these we've been over, but some of them I want to go over again just to make sure we're all up to speed. A solution is homogeneous, and if you say homogeneous, it's okay, but homogeneous, it's a homogeneous mixture if you have two or more substances in a single phase. So a single phase would be liquid, solid, or gas, and what's by all means most common for this chapter is the single phase would be like a liquid phase. So the solutions, you'll take like something solid and place it in something like water. You mix everything up and everything is just a single phase. You don't see like little pieces of solid running through the liquid. There are three types of homogeneous mixtures which are really important to chemists. And those three types are called solutions, colloids, and suspensions. And solutions are by far the most important. We're going to talk about all three, but we're going to focus mainly on the solution because solutions are very, very common and they can do a lot of neat things in chemistry. A solution, also like a colloid and a suspension, solutions have at least two constituents, two pieces that make them up. These two constituents are called solvent and solute, all right? And one part is usually called the solvent and the other part is called the solute. So here, recognize these names. Solution equals solute plus solvent. You have to have both. Now, they all begin with SOL, and SOL stands for something else, which has some kind of bad words in it, so I don't want to say it on video, but anyway, just realize you have to know which SOL you're dealing with. All right, are you dealing with the whole solution? Are you talking about just the solute? Are you talking about just the solvent? And again, we're going to look primarily at solutions where water is the solvent and some kind of usually ionic compound will be the solute. But in that table down there, you can see there's a whole bunch of different examples of how things can combine in different ways. You can have solid solutions where solids mix with solids like the silver and gold. You can also have gas solutions where two types of gases are mixed together. And the air we're breathing right now is technically a solution of gas. You have different kinds of solutes in different kinds of solvent. I would argue that nitrogen gas, which is the main component of the air we breathe, would be the solvent. And oxygen, the important part to us, would be the solute, but it could be interpreted in different ways.
When nickel chloride is added to water, it dissolves readily. Because more nickel chloride could be dissolved in this solution, the solution is called unsaturated.
Some additional terms that will be helpful in this section are unsaturated and saturated. And an unsaturated solution is usually the kind of solution which is most helpful to chemists. And in an unsaturated solution, you can think about it as the solvent has the ability to dissolve more solute if you were to add it. So in that example, in that video, they added nickel 2 chloride, NiCl2, to water. And they added it in, it all mixed up, there's no more solid left, so probably that's an unsaturated solution. We could add more solid nickel 2 chloride and it would continue to dissolve. But there would finally be a point where as we added nickel 2 chloride, it would stay as solid. It would no longer dissolve. And you probably guessed it, that's when you reach the point of saturation.
When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
A saturated solution just means that the solvent can no longer dissolve any more solute. And if you see a precipitate, as in a precipitation reaction, you have gotten to the point of saturation. Now, water is a really good solvent, but there are some compounds like lead 2 iodide in the video there, the yellow stuff. It just can't handle that much PbI2. It saturates really fairly easy, and it becomes a solid. On the other hand, in the previous video with the green nickel 2 chloride, water can handle quite a bit of nickel 2 chloride. It'll dissolve before you reach the point of saturation where a solid appears. So if you see a precipitate form, that means you've passed the saturation point and solids begin to appear. On the other hand, unsaturated just means you can add more solute and it will in theory still dissolve.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid. Some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
There's also what they call a supersaturated solution, and supersaturation isn't as common, but I did want to throw it in here. Supersaturation, how they usually do this is they'll take some kind of solute, and in this case it was a sodium acetate, I believe, and they place it in water, but they heat the water up to maybe like boiling or 50 degrees Celsius or something like that. And generally speaking, as temperature goes up, you're able to include more solute before it gets precipitated. So they have this hot solution with a lot of sodium acetate in it, and they very slowly cool it down. So it looks just like water. However, if you disturb it, all right, and what they did in the video is they had a seed crystal of sodium acetate, and that disturbed it, so the precipitate started coming out. In the lower picture, you can see how there probably was like a scratch on the beaker, or maybe they bumped it, and actually you'll begin to see solid form right away that way. But anyway, if you have some kind of a disturbance, then wow, precipitation just starts going crazy. It just like pops out of thin air. This is the supersaturation process, and there are some kind of neat uses for it. For us, though, it's just more entertaining. I think that's kind of cool how they can build that little structure of sodium acetate, but I am a chemist. Other definitions which are important include miscible and immiscible, as well as solubility. So miscible just means that two or more, usually liquids, mix together well. They're soluble, all right? If you have something which is immiscible, that means they don't mix well and they'll separate. So as an example of that, if you're 21 and over, 19 in Canada, you can add ethanol, which is basically drinking alcohol, to water, and you can make a mixed drink, essentially. That would be two miscible solutes, two miscible liquids coming together. On the other hand, if you try to take something like oil and place it in water, they don't mix very well at all. So oil and water you would consider are to be immiscible. Solubility is another term. Solubility is literally a number that's associated with how much solute can dissolve in a solvent at a specific temperature. So it's usually referenced in grams, sometimes moles. And the graph down there shows the solubility of several compounds. Right about 40 grams per 100 milliliters on the y-axis, there's a kind of a yellowish line for sodium chloride. And you can see it just goes straight across. It is getting a little bit bigger. So that means is that as the temperature, the x-axis increases, the solubility of sodium chloride increases as well. And most of the compounds on there increase the solubility as temperature goes up. So you can see as you go left to right along that graph, most of the lines are getting bigger. Like glucose goes crazy, the sodium acetate goes crazy. However, on the bottom is a compound called cerium sulfate, and cerium sulfate solubility decreases with increasing temperature. So most of these will increase their solubility with greater temperature, but there are some compounds like that cerium sulfate thing that actually decrease their solubility with temperature. We'll talk more about why that's the case in Chem 223. There are some factors that affect solubility, like why some things are miscible and why some things are immiscible. And chemists like to use the idea a lot that like dissolves like. And what that refers to is that as the intermolecular forces of the two things you're mixing get closer to each other, the more likely they're going to mix. So earlier I used the idea of water and ethanol, drinking alcohol. They mix really well. They both have hydrogen bonds. They're both very kind kind of similar on a structural level, no problem. On the other hand, oil and water don't get along very well. Oil is generally nonpolar, and nonpolar things don't get along very well with superpolar things like water that even has hydrogen bonds. On the other hand, if you mixed oil with, say, pentane, those are both essentially nonpolar substances. Those would probably mix pretty well. In the little graph there down below, we have a series of alcohols. So the first one is methanol, like we saw in the OChem chapter. Ethanol, the drinking alcohol, is next, followed by propanol, etc., etc. And what's interesting are the two columns. So the first column shows the solubility in water and the OH group on the alcohol, they get along pretty well. But as you can see, the solubility is going down. Like by the time you get to butanol, it's not infinite, all right, a little bit less, although still pretty good. Pentanol less, and hexanol is the least of all. On the other hand, C6H14, which is hexane, methanol doesn't dissolve very well at all. But you can see the other alcohols dissolve pretty well. Hexane is nonpolar, all right? It's considered more nonpolar than anything. As the alkyl group gets larger, it becomes more like C6H14. It becomes more like a nonpolar substance. So as the alcohols get bigger, they actually are better dissolved in nonpolar solvents like hexane than they are in water, which is kind of an interesting thing to think about. This is a joke I couldn't resist. You can see the poor polar bear. Polar bear goes, "Help, help, I'm dissolving." And the brown bear goes, "But bears are insoluble." Bears like swim in the ocean and lakes and stuff like that. But then poor polar bear goes, "That's easy for you to say, you're not polar." So polar bears would dissolve in polar water, all right? Duh. Anyway, I know I need to get a life, but I couldn't resist. Like dissolves like is the kind of thing to think about. And if you have to guess, like dissolve like is what you want to do. So here's some examples of combinations. So water and acetone get along pretty well. Water is polar, acetone is polar, so probably that's a pretty good mix. The second example, benzene, which is C6H6, it's the circle of carbon compounds, dissolves in toluene, which is methylbenzene. Those two are both pretty similar. They're basically nonpolar, so they would have induced dipole intermolecular forces. But if you try to mix benzene, which is very nonpolar, induced dipole intermolecular force, that wouldn't dissolve very well in water because water's intermolecular forces are quite different than benzene. Water, again, is polar with hydrogen bonds. They probably wouldn't get along real well. We're going to talk more about solubility in Chemistry 223. We'll talk about some of these phenomena, but with these kind of terms under your belt, we can now get into the idea more about what's happening with solutions. Here's a question you might say. Which of the following solvents would you expect lithium chloride to be highly soluble? So if you put lithium chloride in each of those, which one would it most likely dissolve? Now, if you remember the list of intermolecular forces, the strongest intermolecular force was the ion-ion/metallic force. And lithium chloride has positives and negatives, so that's going to be the ion-ion force. And we want to try and find the compound in the list which is going to be closest in intermolecular force strength to ion-ion/metallic. And you can probably see from that list that one of the options is water. And water, as we talked about, is not just dipole, it's hydrogen bonded. And that is by far the closest molecule in intermolecular force strength to the ion-ion. Lithium chloride dissolves very well in water. That's the ion dipole force that we talked about. If you look at the other compounds, all right, CCl4, CS2, the next one is butane, answer D, and E is benzene. All of those are basically non-polar. They would have induced dipole force. And that's as far away from ion-ion force as you can get. Like induced dipole is the weakest. Ion-ion/metallic is the strongest. So you wouldn't expect any of those to probably dissolve lithium chloride. You would need something with as close to the ion force as you can, and water with its hydrogen bonds definitely closest.